Welcome to Innovate and React. In today's episode, we will look into catalyst research and how DFT calculations can help with that. It's always interesting to see how we can improve conventional petrochemical pathways and find more sustainable options with new catalysts. For this discussion, I'm very happy to welcome back Thomas Bouveyron. He's a PhD candidate at the RWTH Aachen in cooperation with the TH Köln University of Applied Sciences in the field of catalysis. Hi, Thomas.
Hi, Kevin. Great to be back.
Yeah, I'm looking forward to this discussion and learn more about your catalyst research. Maybe let's start with the goal molecule of the reaction you're looking into and what that is used for.
Yeah, so we chose one gold molecule in particular, and that's the n-decanal, but it could also be any non-substituted aldehyde. But yeah, we chose this one because it has great value in the fragrance industry and as a pesticide. It's I think it's used as a fungicide. Mm-hmm. And in the food industry as a flavoring agent, and yeah, its conventional route is quite interesting to look at and maybe to improve.
Mm-hmm. How is it made industrially?
Industrially, so far, it's like almost all chemicals starts with crude oil, where ethene is then further synthesized through the shop process to an octene. And through further steps, then hydroformylation to n-nonanol, dehydration to n-nonene, and at the end, through another hydroformylation step, you get n-decanal. So all in all, every step is based on petrochemistry, and well, the waste is very high, and it's very long and not very ecological or economical.
Yeah, very, very many steps. Because in the conventional route where the hydroformylation is used, hydroformylation always is a C1 extension, and it's difficult to get the aldehyde without that. And here you start with the 2 carbons less because you get those from the shop process, right?
Yeah, exactly. And because we start from ethene and then through the hydroformylation, you always get the even numbered aldehyde at the end. So, for example, if you wanted to get odd numbered aldehyde, it would be quite more difficult.
Yeah, exactly. And these aldehydes, as we discussed, they are used in the industry as a fragrance because they have a nice lemony flavor or smell.
It's right? A citrusy smell, and n-decanal in particular, and that's one reason why we chose it, is one of the scents in perfumes, like for example Chanel No. 5.
Interesting. Yeah, that's then already a pricey product.
Yeah, exactly.
But with many reaction steps, and ideally we could use less when, according to the principles of green chemistry, it's always best to reduce reaction steps, use catalysts. What other principles did you apply in the change of the reaction?
One more thing is always to try and substitute the petrochemicals. So the conventional route starts from crude oil, and it would be nice if we could start with bio-based chemicals. And that's exactly what we did with the help of Verbio GmbH. They provided us with the terminal alkene and decane, which they got from the ethanolysis of oleic acid methyl ester from a plant. So
there you directly get the C10.
Yes, exactly.
The C10 building block. And now you want to attach an aldehyde function to that. Yeah. What reaction did you look into then?
So we, as you said, we have the C10 alkene, and it's basically just a direct oxidation at the end of the double bond. So the first thing that comes to mind is the Wacker oxidation, which is a well-known reaction that has been used for quite some time. I think it's over 100 years now. But direct oxidation at the terminal carbon of a double bond is always difficult, because there is a rule that most chemists know, and it's called the Markovnikov rule.
Yeah.
And that's one of the main challenge we try to face in this project, because the second carbon, so the highly substituted carbon, would be preferred in the direct oxidation.
That is the Markovnikov.
And that's the Markovnikov rule, exactly.
Yeah. And your goal is to have the linear one, which has to be the anti-Markovnikov, so the non-favorable product.
Exactly.
And how did you manage to change the odds for this reaction?
Well, so first of all, we looked into literature, because it is known and it has been tried before, not with the linear unsubstituted alkane so far, or not in this extent as we did. There are in literature some experiments that used aryl substituted alkenes, such as styrene, for example. And there the styrene group would direct the anti-Markovnikov selectivity. But for us, there is nothing in the molecule that can help with that. So we have to look at the catalysts and the conditions of the reaction themselves. And so we started off with the one factor at a time optimization. So we took literature experiments and tried to replicate that for our substrates. And we found one catalyst that worked pretty nicely.
So you started with the reaction conditions from like a styrene paper? Or?
Yeah, basically. So there are more than these styrenes. There is a few literature about the modified Wacker oxidation, and they're all in agreement with each other that this catalyst, the palladium chloride bis acetonitrile, works pretty good for that in the highly substituted alcohol tert-butanol as the solvent, in comparison to water and hydrochloric acid used in the conventional Wacker oxidation.
Yeah, the conventional one, I think, is done with ethene, where you basically don't really have a different product. You always get one product because both carbons are the same.
Yeah, so there is an example that most people would know that is used in the Wacker oxidation, and that would be the synthesis of acetone, where it is the Markovnikov product at the end, where you start with propylene.
Yeah, exactly. And then you apply this reaction conditions to the new substrate, which is the n-decanal. And but from the theory to a working reaction, that always takes time, as we all know. How did you proceed to start with your reaction and with the new substrate to then basically have a working reaction in the end?
Yeah, so I took literature, as I said, and just tried it at first, see if it even was possible, or if I had to change basically my whole PhD idea. Lucky for me, it worked. The reaction was nice to me, but it didn't work very well. So I started off with selectivity towards my desired aldehyde of, I think they were 8% or something. So not very good, and the conversion was also not very good. So I started to change in one factor at a time manner all the reaction conditions, and found some trends that I could not explain quite yet. After that, I turned myself to statistics and tried to find a more organized approach to reaction optimization, and that's what we did. We used design of experiment and found even more questions and even more problems than we expected at the beginning, but that helped us to get in the right direction to optimize the reaction even further.
Let's recap real quick. What is the design of experiments in this context?
Yeah, so I used Minitab as a program, and I chose 7 different factors, So the catalyst amount, the co-catalyst amount, substrate amount, water content, reaction time and reaction temperature. And the outcome of my statistical design was the selectivity and towards the aldehyde and the conversion of the alkene. And basically the program gives you an experimental plan depending on what you chose as a difficulty or a precision. And then it tells you what experiments you should do at what corner points of those factors. And it looks at the best outcome you want to give him, or the reaction gives you, and then it tells you where the optimum of your reaction is based on the outcome you got.
So a statistical approach that uses not only the exact points to measure, like you mentioned before, the classical 1 point at a time reaction, you can only catch what is in the points you measure. But with this, as I also use the design of experiments in my PhD, is that you can also find optimal points in between the points you measure, because there are some curves in the program that gives you a local optimum. Yeah,
and you also can find codependencies in the different factors between one another. So maybe your temperature and your substrate amount are together influencing your reaction, and you cannot have the effect of one without having the other one. So that's also nice to have, because in a one factor at a time you would never see such dependencies.
And you also can find factors that don't have an influence at all, and then in future experiments more or less set them at one point and then test with others.
Leave them,
to also reduce the amount of experiments necessary to find the optimum.
Yeah, that's also a good point, because we chose a model where we only had to do, I think it was about 50 experiments, which is quite a lot when you think about the palladium catalyst. But it could have been way more.
Yeah, with 7 parameters, when you combine each parameter with each, that's way more.
That's a lot, yeah.
Quick break for 2 things. First of all, a big thank you for tuning in. This really means a lot to me. And the other thing is, please follow Innovate and React on whatever app you're listening. This really helps to grow the show and get new guests on to continue. Thank you so much for your time. Back to the episode. You mentioned new challenges that you found from this design experiments. What were those?
So what we found is, in that what we observed also in our first preliminary tests, is that we need too much of the catalyst. So we are not in a catalytic environment, but rather in a stoichiometric environment. So we needed way more catalyst, and also co-catalyst, the copper chloride which is supposed to reoxidize the palladium chloride at the end. And we needed too much of those. So that was a big problem and a big question we had to answer. And surprisingly enough, the reaction required very low temperatures. So between 60 and 80, so we chose 70 basically. 75 was the optimal point. And also water was a critical factor. So basically we found that we need less water, or actually no water at all, for the reaction to work in terms of selectivity towards the aldehyde, which is quite surprising if you think of the original Wacker oxidation, where water is the nucleophile attacking the double bond. So water acts as the nucleophile, and the oxygen from the water attacks the double bond. And for us, that wasn't the case. So where does the nucleophile come from? Where is the oxygen coming from? And there is also literature for that. And basically, they suggested that it comes from the third butanol, so the alcohol, the solvent itself. So that was also a subject that we had to look into afterwards.
So that the solvent is directly involved in the catalytic mechanism.
Yes. And that is chemically speaking, a big challenge because it rewrites the whole Wacker cycle where water needs to first activate the catalytic complex and then is being released afterwards in the cycle and re-enters the cycle and everything. So that was also a big mechanistic question that was opened due to the DOE finding.
Interesting. And then with your results from the DOE, you knew which parameters are critical for the reaction, and you had an optimal point for the reaction conditions. But the mechanism of a reaction is always something to look at to really understand what to improve and what to change to get better results, right?
Yes. So, and that is quite surprising, with the Wacker oxidation, because it is a rather old reaction and it is used commonly, or was used commonly in the industry, but not all its steps in the cycle are really well understood. So there is a lot of debate, for example, at the end, if the last step is a beta hydride elimination or a reductive elimination. And for us also, the nucleophilic attack can happen in two different pathways. So the water, as I mentioned before, can come from inside the complex. So the complex was activated with water before, and then the attack happens from inside. This would be an syn attack. Or it can happen from outside of the catalyst, where water directly attacks the double bond, being an anti-sphere attack. And this is also a subject of some debate. And as you can tell, it is not very easy to get everyone under one roof and agree about the mechanistics of the reaction.
Yeah, maybe to also, I think with these mechanisms, especially, it's sometimes difficult to just explain them with words. So I will put in the show notes a link to a picture of the different mechanisms. Yeah, coming back to the water is one option, but you also said that solvent can interact there. How is that different?
Yeah, so we did different tests with different solvents. It was clear that alcohols were the way to go, because there are in literature tests where 18O markings were done and inserted in the solvent, also the alcohol, and this oxygen was then found again in the products. So that was the proof that oxygen came from the solvent. So we did different testing with methanol, ethanol, pentanol, and then highly substituted alcohols. And in the first phase, we only went to terbutanol because it is the highest substituted alcohol at the relevant group, and it worked quite well. And later on, we found that this solvent has a few disadvantages, because aliphatic alcohols can undergo dehydration, building a carbonyl ion, and then be turned into either in the presence of halogens. The halogen can attack the carbonyl group, or it can turn into the alkene itself, and those have a boiling point way below our reaction temperature. And that's actually what we observed. We had a big loss in relevant solvent, which, as you said also before, participates in the reaction.
But that would be the way you don't want it to participate. You want it to just help the reaction, but then stay the solvent.
Yeah, exactly. But it's a double-edged sword, because it's nice that the solvent is there and helps the reaction, but also that means that the reaction is consuming itself, basically. So that is one thing. And
they would also lead to other side products and probably more difficult separation, and you lose solvent, and that all is, when you want to scale up such a reaction to an industrial level, is not really beneficial.
Yeah, it's also funny that you mention the separation, because we get the ketone as well, and decanal and decanone are quite difficult to separate from one another. So that's also an issue that we are currently looking into, and that will probably take a longer time to perfect.
So a perfect selectivity would be also great for that purpose, because then you don't have headaches for the separation.
Yeah, so that's the thing that's so difficult is so we know which parameters are relevant. So the use of those alcohols, now we are trying tert-amyl alcohol, which is basically tert-butanol with one methyl group more, so one chain length more. And it already worked way better with an improvement in selectivity also. So that's one aspect we're looking into. And the catalyst itself, so the complex, the bis-acetonitrile, is also very important. The copper chloride takes also part, because there are literature that suggests that the copper itself is forming a bimetallic complex, and that also reduces the activation energy for the desired reaction towards the aldehyde. So there are a lot of factors taking place that all need to work very well together for the selectivity to be high and the reaction to work.
And for this you would need a much better understanding of the catalytic mechanism to see where you can tweak, where it's decided whether you get the Markovnikov product and the anti-Markovnikov product, to tweak those positions in the catalytic complex to favor one more, right? And how did you look into this?
Yeah, so because we were spending a lot on catalysts and on reactions and everything, we turned to modeling, to computational chemistry, and more precisely to DFT calculations.
Maybe a quick recap, what does DFT stand for?
DFT stands for Differential Functional Theorem. So basically what the program does is calculating the state of all the electrons in your system. So the system has a database of how many electrons carbon and all the elements have. And it looks at an energetic minimum, depending on what you want the program to do. But yeah, basically it goes through all the states of all the electrons and looks for a minimum in energy. And then you can optimize your geometries or find transition states for your reaction. And basically that's what we did. So we looked at dissociative ligand exchange for the minimal geometries of the different steps. And then we looked at the transition states of the different types of reaction. And we compared the classical PDCl4 catalyst with our new catalyst for two products in two different reaction pathways. So yeah, it were a lot of calculation involved.
Yeah. And then to break it down maybe a bit, so you take these complexes and then you do a virtual reaction, or do you just take different states that you configure and then you compare those?
A bit of both, I would say, because we take the optimized geometries of the different states of the reaction. So if you look at the cycle, there are different stable steps, and there is a transition state in between all of those steps. And what we did is we used Gaussian. And a special thing in Gaussian is that you can use a QST2 type of calculation. So you give the program the first optimized geometry of the educt and then the geometry of the product. And then it moves along all the different geometries and finds the pathway from the first one to the second one and gives you the energy of the transition state. And that's what I looked at, to find the lowest energy for the best pathway with the best catalyst for the AM product.
And what different transition states did you find? What were the conclusions of those?
We chose, or we identified the nucleophilic attack as the critical point in the reaction, either if it's for the decision if it's going to be Markovnikov or anti-Markovnikov. So logically where the nucleophile attacks is where the oxygen will be at the end. So we looked closely at that and did all the calculation for the different solvents. So we also used water as a possible nucleophile for the two catalysts. We used tert-butanol, tert-amyl alcohol, and compared the energetic difference of the activation barrier between the different transition states to ground states.
And you found that the bigger the nucleophile is, the better it works. I mean, if you look at the nucleophiles you just described, it's like they get more bulky.
Yeah,
right?
so interestingly, what we found is that for our purposes, it's very well aligned with the experiments that the palladium chloride bis acetonitriles lower the activation barrier for the desired product. But we were quite frustrated until recently because the Markovnikov pathway was logically always preferred. So we could only argue with the lowering of the activation barriers while we would observe what we did in the lab and compared to the calculations. Until recently, where I did all the calculations for the two alcohols, where not only the activation barrier got way lower, but also the gap between the two different product pathways was lowered quite substantially, explaining why more of the other product would also be formed in comparison to the other. And for the bigger alcohols, the bigger the alcohols got, the better the energy was for the anti-Markovnikov product. And starting with the tert-amyl alcohol, we firstly observed an inversion of the energies and that would prefer anti-Markovnikov after the first relevant transition state. So not only is it energetic effect due to the catalyst, but also probably a steric effect of the nucleophile itself, because a big nucleophile, when the catalyst is on one carbon, then the bigger nucleophile would prefer being at the end of a molecule rather than in the middle.
Yeah, I think that's often a way to go. That's also in the hydroformylation, how you can also improve the N to iso products. I think it's a bit similar here. But you also mentioned the acetonitrile ligands in this complex.
Yes.
Did you try other ligands or just these?
We tried a lot, actually. So in the first phase, I had students synthesize a bunch of different ligands, and I bought all the kinds that I could get, also those ones who were already finished on the palladium. And we tested ylides, ferrites, and all phosphonates and everything. And we found that the connection between nitrogen and palladium was the most important, because we're in comparison to acetonitrile and benzonitrile, we also tried cyanides, so where the carbon and not the nitrogen is on the palladium, and those worked not as well, and I don't remember quite well, but I think they didn't work at all. So that's one thing. The other thing is, maybe we can talk about that later, that these ligands have a problem. They work well, but they get lost in the process also. So another factor to take into account. And that is also one thing that we found in our DFT calculation, is that chloride as a ligand is always preferred to be on the palladium. Okay. So we have catalyst fatigue, and that would also explain one of the factors we saw in the design of experiment, that lower temperatures and lower reaction times especially are better for the reaction, because after half an hour we could only see in the MS the chloride type palladium catalysts and none of the acetonitrile, but the acetonitrile being the most important thing because it directs the reaction towards the AM product. So
So the chloride comes from the copper chloride?
Yes.
And did you then try other copper species, or what's the solution for that?
That's basically our thought process. Is we saw, okay, the nucleophile is important, the catalyst is important, but we lose both of those. Mm-hmm. And one big problem would be the co-catalyst, mm-hmm. because the co-catalyst regenerates the catalyst species that we don't want, and that is always energetically preferred. Mm-hmm. So we tried without copper chloride to begin with, didn't work. We tried the ligand itself as regenerative additive, mm-hmm. so acetonitrile in the reaction, didn't work. In literature, there's also benzoquinone as a co-oxidant, worked okay-ish, I would say. So we tested also different copper sources and different chloride sources, and the results of those tests show that copper is quite important. Mm-hmm. And that is probably due to this bimetallic complex forming that lowers the energy. We didn't look far into that because we had to look at all the other factors before that. But based on those observations, I would say that we agree with what literature tells us.
And what was then the key to solve this problem? I mean, if the copper chloride makes you lose ligand and solvent.
Yeah, so that's not where we're at right now. We don't have the solution right now. So we are still trying to figure out where we can optimize the reaction and where optimization would maybe influence another thing that would then lower the selectivity. Mm. And I would say our big success in this project so far is that we did understand the mechanisms. We did understand what is important in the complex and how the complex activates the alkene and how the nucleophile takes part in the reaction. Mm-hmm. And that was a bit difficult to come to this point of understanding. And now we are trying to see what we can do about those. I think that will not be me because I'm at the end of my PhD right now. But the group where I'm at right now will continue the project and hopefully find a solution to all of those.
Yeah, that would be great. One other thing that I find also interesting about this reaction especially is that you have two catalysts, basically the main catalyst and the co-catalyst, they have to work together. And in the main Wacker oxidation, when you use it for ethene, I remember from when we did in the practical course, we also used this reaction as an example with bubble columns, and then there were two separate reaction chambers, basically. One where there's the oxidation of the alkene happening, and one where there's the regeneration of the catalyst happening with oxygen. But what was your reaction setup? Did you also have two reaction chambers, or did you have just one?
Yeah, so we did all of our testing in one chamber, so one very simple setup with a flask and a cooler on top, and left it at that because we needed to see what was happening all together. And there is another problem for using the reaction in the setup you described, because the classical Wacker oxidation has the advantage that the products that are being generated have a lower boiling point than all the rest of the components. And so if you get acetone, for example, in the reactor you described, then the acetone would evaporate, and then all the reaction mixture with the catalyst and everything can be transferred into the second reactor, be regenerated, and then be reused in the first one. For us, that's not an option, so that's also a challenge that we face, and that's also a reason why higher substituted alcohols would be better, because our products have a boiling point, so the n-decanal, I think it's 290 7 to 9, and the ketone is 211, which is way higher than anything else in the reaction. So there needs to be another separation step for us.
Do you have some in mind that you would try? Or?
We did a few testings for that. So we were hopeful that we could get around protecting groups, and that would not be the case. So we tried flash chromatography. So we tested different kinds of solvents to try and separate those. Interestingly enough, only methanol or methanol containing solvent mixture worked for the separation of ketone to aldehyde. And what we think, we did not look that far into that, but what we think is that the column and the methanol are reacting and forming this sludge that protects the aldehyde group, and then therefore separating the two. But yeah, that's not a great option, because then you have to unprotect the aldehyde to regain it, and that would add a lot of steps that are not very welcome if you think of the conventional route that we talked about at the beginning. So you want to keep all the steps fairly easy and simple and not a lot, and
well, there is a reason why this conventional method is still applied, I guess.
Yes.
But chromatography is also, in industrial contexts, difficult. Maybe with these higher priced products, it could be worth it, but usually one would try to avoid that.
Yeah, that's why we left this this section to the side for now, because we first want the reaction to work before we think about separation and process development. It is possible, and we're very positive that it will be possible.
Yeah.
And
but it's a different problem.
But it's a different problem, yeah. And even for the chemicals we have, so the decanal is a fine chemical that is very high priced and sold in low amounts. So it could be worth it to do it that way, but I'm sure someone will find something and solve that problem too.
Yeah, definitely. That's some also engineering problems for later.
Yes.
And
Rome wasn't built in a day.
Yeah, exactly. Yeah, I think then we can come to an end to this discussion. And I think since our last discussion here in the podcast was before I started this closing tradition of the question, what is your favorite discovery in chemistry? And you may answer it now.
My favorite discovery in chemistry, it's very basic and maybe a bit childish, I think. But I always found the story of phosphorus very interesting, because when I was a child, I watched a lot of videos on YouTube of these theatrical chemists' lectures, and there was one where they explained how white phosphorus was found, and they let the thing on fire, and it illuminated the whole room, and it came from alchemists that distilled, I think it was urine from horses to try and find gold, and they so happened to find phosphorus, and with that the oxidation reaction of phosphorus on air, where it lets itself on fire, and that's where the name comes from Greek phosphoros, which means light bringer, and I find that quite poetic.
Yeah, definitely. That's also the whole discovery of the element is interesting story.
I think it shows how science works. You try one thing, even if it's very absurd, and you end up finding a whole other thing that will have use and understanding later on.
Yeah, that's also a thing, like back in the days when they really started to discover one element by the other, it was really that even one person could make major discoveries, which is not really that easily possible anymore.
No, yeah.
Teams of researchers.
Definitely, yeah. And to find an element nowadays, I think you have to be some kind of physicist with access to very expensive tech.
Yeah, but still, there are very interesting discoveries in chemistry still to make, and I'm looking forward to all these new discoveries that will come up.
Yeah, me too.
Yeah, thanks for this great discussion.
Thank you for having me.
Also, thank you so much for listening. Check out the show notes to learn more about Thomas's research. Let me know if you would like to talk about your own research in Innovate and React, and send me an email to contact@innovateandreact.com or find me on LinkedIn. Again, a follow would really help as well. Until next time, stay curious and keep innovating.